Look at the sheer mass of an electric locomotive. Moving hundreds of tons of steel from a standstill takes enormous, continuous kinetic energy. This diagram shows energy reaching the wheels. Alternating current from the grid passes through a gateway to become a steady stream of direct current driving the motor. That gateway is a passive rectifier bridge. It uses diodes, one-way valves allowing power to only flow forward. While the train accelerates, the system works perfectly. The motor pulls continuous current from the grid, spinning massive gears to build incredible forward momentum. Keeping heavy industrial equipment moving requires a relentless one-way consumption of electricity. You pull power from the grid, and you turn it into physical motion. But when an emergency requires an immediate stop, all that built-up momentum must go somewhere. The wheels lock, metal strains, and the physical force reverses. On this diagram, the motor instantly acts as a generator. It takes the train's kinetic energy, pushing a massive direct current surge backward. The surge hits the one-way diodes, which slam shut. The completely blocked energy is forced into the DC link capacitor holding tank. If that capacitor takes on too much energy, its voltage will rapidly spike past its design limits, causing the hardware to physically rupture. Bringing heavy equipment to a halt requires managing a highly destructive wave of trapped electricity. To prevent an explosion, engineers traditionally added an emergency release valve known as a brake chopper. It opens here, diverting dangerous voltage away from the overloaded capacitor. The chopper forces trapped current through a massive resistor, intentionally destroying the power by burning it off. Instead of being saved, all of the kinetic energy from the massive moving train is converted entirely into intense radiating heat. Throwing away gigawatts of potential electricity simply to stop a machine is an unacceptable waste in modern engineering. This diagram illustrates the hardware solution, the naturally commutated 4-quadrant dual rectifier. We now have 2 complete rectifier bridges placed side by side in an anti-parallel arrangement. The green forward bridge handles standard acceleration, while the blue second bridge provides a dedicated pathway exclusively for backward-flowing power. When the train hits the brakes, this reverse bridge captures the high-voltage direct current and precisely steps it back down into alternating current. We solve the bottleneck with a two-way street. But wiring 2 opposing high-voltage gateways together introduces a severe operational risk if both open at once. If the system pulls power forward and pushes power backward at the exact same millisecond, the resulting short circuit will completely destroy the drive mechanism. To prevent this electrical collision, the system uses a software mechanism called lockout time. As shown on this timeline, that gap is a mandatory pause. The forward bridge shuts down, enforcing a split second of total darkness to clear all valves before the reverse bridge ignites. Bidirectional power relies entirely on the precise mathematical synchronization of that empty void between forward and reverse. Looking at the complete diagram, you can see the braking energy that was previously trapped in the capacitor now safely drains out through the reverse bridge, smoothly converting back into an alternating wave. That recovered electricity flows out of the industrial machine and matches the frequency of the incoming supply to merge right back into the power lines. The public grid then catches that recycled electricity. It travels up into the high-voltage transmission lines and is immediately redistributed to power other homes and businesses. By engineering a seamless mirror for our electricity, we stop wasting the momentum of our heaviest machines and start actively recycling it back to the world.